I would like to introduce Dr. Sergei Tolmachev, the current director of the United States Transuranium and Uranium Registries. He is also associate professor in the College of Pharmacy at Washington State University, and he was one of the world's leading experts in actinide analyses. So if you'll please help us welcome Dr. Sergei Tolmachev.
Good morning, everybody. Thank you, Carol, for a nice introduction. So in this presentation, I will carry head of not as a director of USTUR, but as a radiochemist. I have a background in radiochemistry. So, and this presentation is about total skeletal estimation of actinides in a total skeleton. So the goal is pretty simple: how we can estimate total skeletal activity of actinides, plutonium and americium. So there are basically two approaches you can do. It's analysis of the entire skeleton or analysis of limited number of bones. So in USTR, as Ron mentioned in his presentation, we have two types of donation, like what we call whole body donation and a partial body donation. So of course, if you have a whole body, it's pretty simple. So you have an analysis. What we are doing, we are analyzing the right side of the skeleton, and then we calculate activities in even rib and even vertebrae, and then we multiply by 2, assuming the symmetry of a skeleton. So when you have a partial body case or donor, so the skeleton activity is a function of two variables. One is the mass of the skeleton, and another one is the concentration in the skeleton. So we usually analyze in like a few bones. So, and there is two ways you can calculate your skeletal weight. One is based on ICRP formula, which is a function of height. So usually in USTR we know the height of our registrants, so we use that formula. So in case if you don't know, so you can use a standard reference man weight of 10.5 kgs recommended by ICRP. So we will talk about, we will have a presentation from Maya Afton-Dilashvili right after me, and we will touch basis on how to estimate skeletal weight. So what is the pro and cons for two approaches? So if entire skeletal analysis is probably the most accurate estimation of skeletal content. So the cons are very limited opportunities. I don't know if there's any other place besides USTR when you can do this. So there are large numbers of analysis you need to perform. It's from 70 to 100. And if you go into limited bone analysis, so then you have it's a typical scenario. That's what people usually take in autopsy. If you remember, 5 bones we took from McCluskey case. So, but the question is, how accurate is your estimation? So its problem is not new. There are several papers published in the literature how people estimating the skeleton activity based on a limited number of samples analyzed. So I found this paper from Tim Lynch, and actually published in 1988, when they studied the distribution of plutonium in skeleton using 4 USTR whole body cases. So in this they give this nice table. Actually, there's a table with how many percent in each compartment of skull you can of activity. And what I figured out was nice of patella. So for those who don't know what is patella, so patella is kneecap. So actually I learned it myself when I started to do work at USTUR. So what is a good thing about patella? So it's easy to collect at autopsy. So it's a single bone analysis. So there is a simple direct scaling to total skeletal activity. So there is no estimation. So it's a direct estimation of uncertainties, just basically based on your analysis. So the drawback, the cons was that it's not commonly taken at autopsy bone, even at USTUR. So in this study, I used 17 USTR cases. We have more than that now, but so we're primarily exposed to plutonium, and plutonium, 2 cases were from plutonium-238 exposure, and 15 cases were exposed to plutonium-239. So in all americium we measured in our samples was a decay product of plutonium-241. So it was no exposure to plutonium-241. So that's kind of a difference. So, and the post-exposure time was varied from 15 to 55 years. and we calculated what I call deposition coefficient, which is a ratio of activity in patella divided by activity in skeleton. And we used two approaches to estimate total skeletal activity. One is just direct scaling from patella measurements. Another one when we did some mathematical log transform regression analysis. So before we'll go further, I will make some assumptions. I want to state my assumption. So that's the deposition coefficient. This is a ratio is independent of route of intake, type of exposure, material type, treatment, years post-exposure, and the skeletal pathology. So that's the first approach, is deposition coefficient. So as I mentioned, I have 17 cases. It's a little bit busy slide, but I want to put everything in one place. So we calculate K-depths for each individual radionuclides for 238, for 239, and for americium 241. And you have and we test for outliers. There was no outliers. And we did some comparison tests between plutonium-238 and plutonium-239. So if you can see, there was no statistical difference between two isotopes, which is not surprises me, but I know there are people even in this audience who is thinking that there's a difference between two. I'm not going to discuss the thing here. So, and anyway, so using three isotopes, I defined three equations. So if you believe, if you want to use just for plutonium-238, you think it's the right way to do, you can use upper equations, so middle for plutonium-239 and for americium-241. So, but my goal was, okay, guys, I have 17 cases, so how can I improve my statistical power? So can I combine this data together? So, and what we did, I just repeated ANOVA test. So basically, it's a parity test, but you can compare all three radionuclides, and what I figured out, there was no statistical difference between these three sets. So I was say, okay, I will combine them together, and we'll calculate the K-depth based not on the 17 data points, but on 51. So, and I was able to derive this equation for americium plutonium skeletal activity using patella. So the second step was to do some regression analysis, and since data were not normal, so we have to go through a log transformation. So I notice it's exactly the same approach I take as a first step. So for all three radionuclides, 17 data points, so I derive regression analysis lines. So, and you can see those regression coefficients in the table, so excellent correlation, which is not surprising. And but then the next step was same. Can I combine them together or not? So, and what we did, so I did statistical tests checking on the slopes and an intercept between if they're statistically different or not. So it's figured out that all slopes and intercept are not statistically significantly different. So I said, okay, I have a right to combine it together and derive this line. So this is for a combined data set of 51 points. So then you can see this regression. So in the next slide is a graphical representation of my data. So first on this slide you can see this is activity in patella we measured, which is for for a plutonium-239. And as you can see, most of the data points they are above 0.1 becquerel. So, and there's two data points which is in the millibecquerel area. So this is two cases when people were exposed to plutonium-238. So the activity of plutonium-239 was low. So if you add plutonium-238, so then that's a picture like this. So now it's opposite way around. You can see that most of the data points are going in the millibecquerels. I'm talking about patella activities in the millibecquerels region, while only 2 points is going up to becquerels area. So those cases where people were exposed to plutonium-238, so you have a high activity in the patella. But there are still some, disconnection between two areas. So, but when you add americium-241, then you can see this is a nice data set which covers activity measured in patella from basically 1 millibecquerel up to 10 becquerels in the patella, so which corresponds from 1 becquerel in skeleton to 1 kilobecquerel in the skeleton. So so when you draw the line, so that's what I use. So you can end up with this equation. So my next step was, okay, guys, I have I offered you two basically way to calculate. One is pretty simple, and another one with log transformation pretty complicated. So question is those two models are that different or not? So I did what they call a mountain plot comparison. And my method number one is simple patella scaling, and method number two is log transformation. And then you can see, so I just want to show you how you can say which one is better or which one is better. So the top of the hill, it should be as close to zero as possible. And on this plot you can see, yes, log transform data, I mean the model, is a little bit closer to the zero, so you assume it's a little bit better, but how much is it really that significant improvements or not? So basically the point is this both models describes, you can derive skeletal activity with a very similar result. So if you let's say in the field and you want a quick calculation, then you say, okay, I'm using this activity in patella multiplied by roughly 300, and you can get the skeletal activity. So if you want to do a little bit more calculations, so you can go to log transformation data and then use a log transform equation from this. So, and basically finally coming to the conclusions. So what we figure out is activity in patella represents about 0.4% of total skeletal activity. So patella analysis allows to estimate actinide skeletal content with a precision about 35%. And when I'm talking about this precision, so I'm talking about in terms of standard deviation, so not 95 confidential interval. So, and another thing which I want to mention, that is no statistical difference was found between retention of plutonium and americium in patella. But I want to emphasize one more time that americium, it was not from exposure, it was from a decay of plutonium-241. Okay, thank you very much.